Today in section 2.1, we're going to talk about the basics of set theory, get some fundamental notation and definitions in our notes so that we can start working with different notations for set theory. A set is defined as a collection of objects that we call elements. A set is defined as a collection of objects called elements. Now, if a set is well defined, and we want our sets to be well defined, if our set is well defined, then the contents can be clearly determined. There's no question whether an element is in the set or not. The contents can be clearly determined. For example, if I have two sets, set A and set B, set A is the set of students in this class, students enrolled in this class, and set B is the set of the three students with the best shoes. Well, which one of these two is a well-defined set? Set A is definitely well-defined. Yes, it is well-defined because I can look at the roster and see who is enrolled in this class. I have no question about whether or not a student's name represents an element in the set A. Set B, however, is a problem because how do we define best? And will your definition of best match my definition of best? When I say best, I might mean the most comfortable, or maybe the ones that the shoes that you can wear all day without your feet hurting, or that you can go walking in. I know that I've had at least one student who was a big sneaker fan, and so best would be the ones that match his definition of really good sneakers. Someone might like expensive shoes or dress shoes or sandals, and those are the best shoes. So this is not well defined because that's an opinion. Different people will include different elements in that set. There are three different methods that you can use to indicate a set. So three different ways to show that something is a set. The first method is the description method. And that's what we just did up there. We just used words to describe what elements are involved in the set. So the description method is really straightforward and simple. The second way to define a set or to indicate a set is what we call roster form. And you can remember that because a roster is just like you call roll from the roster. It's a list. In fact, for the roster form of a set, I'm just listing the elements. Now, an example of roster form, let's write out there. It's a list of the elements. Now, when I do roster form, it is important to use the correct notation. So we're going to say, an example of my set, we're going to do n is equals, and then I have my fancy brackets, and then inside that I'm going to list the elements of n, and then we're going to talk about what all this means. Now first, let's kind of go to the side, and let's say in general, when we are doing set notation, if I have the letter n, the capital letter N, I'm referring to the set of natural numbers. Now, do you remember on our last video, we talked about the different number groups? Natural numbers are the same thing as counting numbers. It's what we learn when we're small. So we start with 1 and we keep counting on. So 1, 2, 3, 4 would be my set of natural numbers. If I have this curved E, that symbol means element. So for example, I could say that 7 is an element of the natural numbers, And I could say that -1 is not an element of the natural numbers. You see how I just put that not slash through. So these are two different ways to use n as my set of natural numbers and that sign for that symbol for elements. So that's just kind of an aside, some notation that you need some to use set theory. Okay, so back to our roster form. I start with the name of my set. N in this case is the set name. I could have named it A or B or C or whatever I wanted to. My equal sign I read as is. And then I know I've got roster form. I'm listing the elements because I have the fancy braces. Inside the fancy braces, I have my list of elements. And my list of elements ends with a ... We call this ... an ellipsis. And an ellipsis means that it keeps going. So my set of natural numbers is an infinite set. It never stops. I can keep counting on forever. Now the ellipsis does not have to come at the end. It could come at the beginning or it could be in the middle. But that ... that ellipsis just says we keep going here. Okay, so 3 methods used to indicate a set. We have our description method where we just use words to describe the set. We have our roster form where we list the elements of the set. And then finally, third, we have set builder notation. Now, set builder notation should remind you of an algebra class. You use set builder notation specifically in college algebra to define some sets. It's a more complex, more structured version of our roster form. Instead of listing out all of the elements, we give some details for them. Okay, so an example for set builder notation. Let's say we're going to have the name of our set is, and then we open up our fancy braces again, and then we say have an X to represent the elements of the set, such that straight up and down line, and then we list whatever conditions there are for it to meet the set. Now, I will do an example here in a minute, but we are going to talk about these pieces. Just like with roster form, we start with the set name, and we say that the set name, so set D is, that's my equal sign, is. And then this X we read as the set of all elements. My up and down line, my vertical line, we read as such that. So the set of all elements such that, and then whatever conditions are here. Let's do an example where we do roster form and then set builder notation. So let's do roster form. Set B in roster form is going to be 11, 12, 13, ... So going on forever. Set B, my elements 11, 12, 13, and then I've got that ... So we can assume it would keep going 14, 15, 16, 17. So this is my natural set of natural numbers. These are all counting numbers. I'm not including decimals or negatives or anything else. But I'm not starting at 1, I'm starting at 11. When I do set builder notation and I give my conditions, those two things need to be indicated. So set B in set builder notation, I start just the same way. B is, set B is, and then I open my brackets and I say the set of all elements X such that, and then I give my conditions. Well, for this set B, X is an element of the natural numbers. I'm not using negatives or fractions or decimals or anything else. And X is greater than or equal to 11. That's my starting place. X is greater than or equal to 11. I could have chosen to say X is greater than 10 instead of greater than or equal to 11. That would get me to start at the same place. So there are 2 different ways to tell what set B includes, the roster method and the set builder notation method. Now we have two more definitions on this first page. First, for a finite set, and secondly, for an infinite set. A finite set either is the empty set, it has no elements, or it has a limit on the number of elements. So the finite set either has no elements, and if it has no elements, we call it the empty or the null set, or it has a limited set of elements. I know how many there are. There are maybe 20, or maybe there's 2036, or maybe there's 5. But whatever it is, there is a limit on the set of elements. Now, the empty or null set can be symbolized in two different ways. Either by opening up my fancy braces and not putting anything inside, that is an empty set, or with the 0 with a slash through it, that means the empty or the null set. Either one of those symbolizes the empty set. So just note that if you do this as a 0, it's wrong. That is not 0. That means the empty set. If I put a 0 in there, that would be an element, and it would no longer be empty. So a finite set can be the empty set, which I also call the null set, or it's a set with just a limited number of elements. Now the infinite set is not finite. It goes on and on forever. Set B up above that we talked about is an infinite set because it keeps going on. It keeps increasing by 1 forever. Okay, let's look at the next page of our notes. We're going to talk about equal and equivalent sets. Equal and equivalent do not mean the same thing. Equal sets contain exactly the same elements. If two sets are equal, they contain exactly the same elements. So it's basically doing the same thing twice. So example of if two equal sets in roster form, if set A is apples, bananas, grapes, and set B is grapes, apples, bananas. These two sets are equal. Set A is equal to set B. They contain exactly the same elements. Notice that order doesn't matter. The fact that they contain exactly the same thing makes them equal. Equivalent sets, however, contain the same number of elements, but the elements don't have to be the same. The equivalent sets contain the same number of elements, which means another way of saying that is that they have the same cardinal number. That's a new term. They have the same, cardinal number. And the cardinal number tells me how many elements are in the set. The number of elements in the set. So equivalent sets have the same cardinal number. They have the same number of elements in the set, but they're not necessarily the same elements. Equal sets are the same, exactly the same elements. So let's add a set C. We've got A and B up above. Now we're going to add a set C, and set C is going to be the set red, blue, green. Red, blue, green. Okay, so let's think about this. When I show the cardinal number of a set, I do it by saying n of A. So lowercase n tells me I want the cardinal number of set A. So how many elements are in set A? Well, set A has 1, 2, 3 elements. The cardinal number of set A is 3. What's the number of set B? Again, same 3 elements. So the cardinal number of set B is also 3. Now let's do set C. My set C is red, blue, green. It also has a cardinal number of 3. Because they all have the same cardinal number, I can say that sets A, B, and C are all equivalent. They have the same number of elements in each of them. But does set A equal set C? Well, no, they have the same cardinal number. A does not equal C. B does not equal C. All three sets have the same cardinal number. They all have 3 elements. But the elements in set C, those 3 elements, do not match. They are not the same as the elements in set A or the elements in set B. So A is equal to B, but C is not equal to A or B. They are, however, all 3 equivalent sets. And we don't have a notation for equivalent. Okay, universal set. The universal set, my symbol for the universal set is a capital U. And the universal set contains all possible elements for whatever we're talking about. Contains all possible elements for a specific discussion. So, for example, if my set I'm interested in is the set of students enrolled in this class, my roster for the class would be my universal set. And then I might identify subsets within that universal set. I could talk about the set of students who are 5'5" or taller. I could talk about the students who are 22 years old or younger. I could talk about the students who are first time in college. Those would all be subsets of that universal set. Or if I was in the grocery store, all of the things being sold in Kroger would be my universal set. The things in the freezer section would be a subset of that. They're still part of the universal set. Everything is in the universal set, makes it a subset. Okay, let's do an example. We're going to say that my universal set is going to be my alphabet, my English alphabet. So I start with A, B, C, D, and I'm going to say we're going to keep going until we get to Z. That's my universal set. There are 26 letters in the alphabet. A subset of that universal set would be the vowels. So this is roster form. My subset A is going to be the vowels. That's my descriptive form. And if I do A in roster form, I would say A, E, I, O, and U. We're not going to include our sometimes Y. So set A is a subset of my universal set because every element in A is also in the universal set. And my universal set contains more elements than just in A, which means A is not just a subset, it's what we're going to call a proper subset. Now, we're not going to list those definitions in our notes yet, but we will get there. Let's do some practice with all of these definitions. Now, remember that you are welcome to pause your video at any time, take a break, come back to it later if you need to. Go ahead and read the top, review the terminology, and answer the question on that example. Pause your video, do that, and then come back. Okay, so that first set A is well defined. I can look it up and see exactly who is enrolled at TCC. The second one, B, is not well defined. Well, why isn't it well defined? First of all, what school? We just said 12th grade. We didn't define if we're talking about all the 12th graders in Texas, if we're talking about the 12th graders at a specific school. What school? Second problem with that is, how do we define tall? What is tall? In my family, tall is going to be somebody over 6 foot. In other families, tall may be anyone over 5'6". Tall is, again, a relative designation. So that means that set B is not well defined. Okay, 3 different formats to identify a set. The first one is my description method, where we use words. We're going to say set C in words is going to be the set of primary colors. That's my word description. If I want to do roster method, I list out the elements. So I set C is, and then I open my fancy braces that I have trouble drawing sometimes. The three primary colors are red, yellow, and blue, all separated by commas. Set builder method, since I didn't use anything numeric, my set builder method is going to be very similar to my word description. Set builder method starts by naming the set is the set of, and then I say all elements X such that, but since I don't have numeric elements, I'm just going to have to say X is a primary color. So that's what set builder notation looks like. Set C is the set of all elements X such that X is a primary color. Okay, now just to remind you, the set of natural numbers are my counting numbers. I start with 1 and I keep going on by adding on 1 forever, ellipsis. It's an infinite set. Inequalities. So inequalities show that something is greater than or less than something else. If you are reading an inequality symbol, this one is less than, this one is less than or equal to. You have your fingers open, right? The one that turns into an L that faces the right way means less than. The other one is greater than. Okay, so this inequality means less than, and this one is less than or equal to. Now, you know it's or equal to because it has part of an equal sign underneath it. It has that second line of the equal sign under, so it means or equal to. Now, this is, so we've got X is less than 5. Then we have X is less than or equal to 5. These are not the same two sets. We're going to take the first one and name it set A. Set A is the elements X where X is less than 5. Now we're going to assume we're talking about natural numbers. So in words, A is the set of natural numbers less than 5, because that is the inequality symbol that I'm using. X is less than 5. That's my description in words. Roster method would be A is, and I open my fancy braces. What are the numbers less than 5? The natural numbers less than 5. Well, would I use 5 here? No, it's just less than. So my natural numbers start with 1. So the set of natural numbers less than 5, roster form, 1, 2, 3, 4. And then I'm going to do set builder notation. A is the set of all elements X such that, and then I've got two pieces of information. X is an element of the natural numbers. And then I also know that X is less than 5. So that is my set builder notation for set A. Now let's do set B. Set B is going to be the set of elements where X is less than or equal to 5. So in description form, set B is the set of natural numbers less than or equal to 5. In roster form, I list out the values. This time I include 5 because it's or equal to. And in set builder notation, I started out like roster. Set B is the set of all elements X such that X is an element of the natural numbers and X is less than or equal to 5. So those are my conditions that have to be met for it to be part of the set. Okay, now we have some more practice down here with roster and set builder method. For each of these three sets, we are given the description and we're supposed to put both the roster and the set builder method. We're going to start over and use this as A, B, and C. So those are my three sets that I'm interested in: set A, set B, set C. I want you to go ahead and, well, you know what? Let's do the first one together. And then I'm going to pause the video. I want you to pause your video to do set B, and then we'll do set C together. So for set A, when we do roster method, we want to list x greater than or equal to 6, where x is a natural number. So I'm just using my counting numbers. Am I starting or stopping at 6? Well, x is greater than or equal to 6, so I'm starting at 6, and I'm including the values that are larger. So there's my ellipsis, because I would just keep going. My set builder notation is going to start: A is the set of all elements x such that, and then I say my conditions: x is an element of the natural numbers, and then I use my inequality statement: x is greater than or equal to 6. So there's my set builder notation. Pause the video, do set B. Okay, set B. It's a natural number and includes elements less than or equal to 4. Well, less than or equal to 4, my natural numbers start at 1 and I get to stop at 4, because it's or equal to, it gets to include 4. So set B includes 1, 2, 3, 4, no ellipsis because it stops, it doesn't keep going. Set builder notation says set B is the set of all elements x such that x is an element of the natural number and x is less than or equal to 4. Then finally we have set C. Now set C is given to us as a compound inequality. We've got two different things going on over here in our inequality statement. We know that x is going to be a natural number, but we've got limits on both ends. I'm going to start reading from x and read back to the left, and then I'm going to start reading from x and read to the right. When I read to the right, it's easy. I've just got x is less than 6. Well, what numbers are less than 6? Natural numbers less than 6 are 1, 2, 3, 4, 5. But then we've got to look at the other end. Now, when I start reading with the x, it's easier sometimes to turn it around and rewrite it with the inequality symbol facing the same way to the x. Notice that it's open to the x here, it's still open to the x here. When I start reading at the x, I have x is greater than or equal to 2. So I have two conditions here. My elements have to be greater than or equal to 2 and less than 6. So I'm looking at those natural numbers that are greater than or equal to 2 and less than 6. So set C in roster form, greater than or equal to 2, so I get to start at 2, less than 6. So I have to stop at 5, because 5 is my natural number that is less than 6. All right, set builder notation. I'm going to use this compound inequality that I was given. I say set C is the set of all elements x such that x is a natural number, and then I just include my inequality statement. It tells me what values to start and stop at. Okay. Or versus and. Or and are my key words in set theory. Or signifies union and signifies intersection. So if I'm talking about or, I have the symbol. It looks like a U, but we don't come back down like we do for universal set. This signifies union. Union means or. If I'm interested in the union, in the or, I'm interested in elements that can be in either set or both sets. So it's the inclusive or. If it's in the union, it can be in either set or both sets. Now here's the way that I tell my classes to remember union. Marriage is a union. Have you ever heard marriage talked about as a union? Well, when there's a marriage union, when I married my husband more than 25 years ago, he brought all of his stuff, all of his belongings, all of his debts, all of his books, all of his clothes, all of his furniture. And I brought all of my stuff, all of my books and wonderful things and all of my belongings and all of my emotions and everything else. And suddenly it's all part of the union, as well as anything we bought together, right? So if it was his, hers, or ours, it's now part of that union. So that will help you remember union. Intersection is what we call when we have that keyword and. Now, U for union, we just flip that upside down as the symbol for intersection. Now, if it's part of the intersection, it must be in both sets. I only include it as part of the intersection if it's in both sets. Well, think about where you hear that word intersection. We hear that word intersection when we're driving. We're talking about driving up on a street. When you come to an intersection, that means you come to a place where two roads meet, right? If I am over here, I am not in the intersection. If I'm down here, I am not in the intersection. To be in the intersection, I have to be in both roads at the same time. This is the intersection. I'm in the intersection here. I'm in both roads. The intersection of sets includes only elements that are in both sets. Okay, my keyword or versus and. For this first one, we have a description of a set that says natural numbers greater than 5 and at the same time less than or equal to 8. So we are only interested in natural numbers that are greater than 5 and at the same time less than or equal to 8. Well, natural numbers greater than 5. I can't use 5, but I can use 6. That is still also less than or equal to 8. 7 is both greater than 5 and less than or equal to 8. And 8 is greater than 5 and less than or equal to 8. Can I use 9? No, 9 is greater than 5, but it's not less than or equal to 8. So that's my roster method. Let's do set builder method for A. Set A is the element of all, or the set of all elements X such that, well, we know that X is a natural number. We were given that. And then we have this compound inequality because we have two limits. My lower limit is greater than 5, so there's my 5. My upper limit is less than or equal to 8. So there's my set builder notation for that set A. Let's do the next one as set B. For set B, we're given natural numbers greater than 8 or less than 6. Remember, or means union. That means I'm interested in either set. It doesn't have to be in both. It can fit in one or the other. So set B, let's see where set B would start. Natural numbers greater than 8 or less than 6. Well, less than 6 is smaller than greater than 8. So let's start there. Less than 6 would be 1, 2, 3, 4, 5. That's less than 6, or greater than 8. I can't use 6, I can't use 7, I can't use 8, but I can use numbers that are greater than 8. So I'm going to do 1, 2, 3, 4, 5. Then I'm going to skip. I don't use an ellipsis because I'm not going to include those values. I use the ellipsis at the end to show greater than 8 keeps on going. But there's just this gap in the middle where not all of those numbers are listed. So this is a little more interesting when we come over here and do my set builder notation. I'm not going to use a compound inequality because I'm not looking at the middle. I've got two sets that don't intersect at all. They don't have anything in common. So I've got set B is the set of all elements X such that we were given that X isn't going to be a natural number. And then we have two different inequality statements that fit in there. So for set builder notation, we've got all elements X such that X is an element of the natural numbers. And then we have two inequality statements. Let's start with the one that is less. We're going to say X is less than 6. Then we have or, so we need to use our union symbol. X is greater than 8. There we go. So X is an element of the natural numbers, X is less than 6, or X is greater than 8. All right, let's discuss the empty or the null set. Remember, my symbol for empty or null set would be the 0 with a backslash, or empty fancy braces. Either one of those works as my symbol for the null set. I have A through F. Pick the ones that represent the empty set. Well, there are 2. C represents the empty set. All elements X such that X is a natural number greater than 6 and at the same time less than 2. There are no numbers that are both greater than 6 and less than 2. That doesn't work. And then E is my symbol for the empty set. D and F each have something inside the set, so they're not empty. This has the element 0. This has the element, that null symbol. For A, X is a natural number greater than 6 or less than 2. That means it has to be one or the other. We have lots of numbers that fit that. B, X is a natural number less than 6 and less than 2. Well, 1 is both less than 6 and less than 2, so that's not empty. Down here with notation is an element of, we've already used before. 1 is an element of the natural numbers. There's an example. Is not an element. I could say -1 is not an element of the natural numbers. I just do that backslash line through my element symbol. A through D, answer true or false. Is 12 an element of that set? That's true, because it would fit where that ellipsis goes. B, 8 is an element of this set. What do you think? This one is false, because if you look at the elements listed, we're only listing odd numbers. 8 is even. C, -8 is an element of the natural numbers. That is false. My natural numbers are not negative. D, 2.5, 2.5 is not an element of the natural numbers. Well, that is true. My natural numbers are those counting numbers, 1, 2, 3, 4. This is a decimal, so it is not an element of the natural numbers. Okay, let's look at the next page. Cardinal numbers tell you how many numbers are in a set. Remember? We represent it by that symbol. If I was asking for the cardinal number of set A, I'd say n of A, the number of set A, lowercase n. So find the cardinal number of each of these sets. For set S, the first set S, ST, ST, S, we keep using those two. So for A, for the first set S, the cardinal number 1, 2, 3 is 3. For B, the cardinal number of that set T is also 3. Oh, no, it is not. I got in a hurry, guys. Look at that. We have 3 things listed, but notice it says the number of distinct elements. Distinct means different or unique. 2 is not different or unique from 2. There are only 2 distinct elements here. Sometimes it'll try to throw you off. This book only counts distinct or different elements. So the cardinal number of this set T is 2. What about C? Well, the cardinal number for this set S is 5 because there are 5 distinct elements. For D, this set T is the empty set. It says T is equal to the empty or null set. Well, there are no elements in the empty set, so the cardinal number is 0. This does not symbolize the empty set. I have something inside. I have one element inside that set S, so the cardinal number is 1. Are any of these sets equivalent? Do they have the same cardinal number? No, they do not. None of those sets are equivalent. Then it reminds you how we defined finite and infinite, and asks for those three sets, A, B, C, if they are infinite or finite. Well, set A is finite, and in fact, the cardinal number of A is 3. There are 3 elements listed. Set B is infinite, though. Because of that ellipsis, it shows that it just keeps going, and so I cannot give a cardinal number for set B. It doesn't have a definable cardinal number. What about set C? Set C is my empty set. An empty set is finite because I can identify it with a cardinal number. It has 0 elements. The universal set, symbolized by that capital U, is a set that contains all the elements for whatever we're talking about. One-to-one correspondence. That's how I can check for equivalent sets. Set A and B are in a one-to-one correspondence if each element of A can be paired with exactly one element of B and vice versa. So we're looking for the sets that have one-to-one correspondence here. Another way of saying one-to-one correspondence is saying that they have the same cardinal number. So count elements. Look to see which sets are equivalent because they have a one-to-one correspondence, which also means that they have the same cardinal number. Well, set A and B, if you look, I can pair those up one-to-one, so they are equivalent. They have a one-to-one correspondence. What set is equivalent to, has a one-to-one correspondence with C? Well, set F. They have a one-to-one correspondence. And then set D and set E have a one-to-one correspondence. So they are equivalent sets. The cardinal number for A is 1, 2, 3, 4, 5, 6. The cardinal number for B is also 6. Set C has a cardinal number of 4, and so does set F. Set D has a cardinal number of 5, and so does set E. That is equivalency, one-to-one correspondence, cardinal numbers. Look at this last example on this page. Which sets are equivalent? A, are these two sets equivalent? Yes. Are they equal? No, because they have the same cardinal number, but they don't have the same elements. What about B? Are these two sets equivalent? Yes, because they have the same cardinal number. They both have 2 elements. What about set C? What about C? Are they equivalent? Now remember, we're looking for distinct or different elements. 1 repeats here, so yes, these are equivalent sets because they have the same cardinal number. They both have 2 distinct elements. What about set D? Yes, they are equivalent, and set D also equal. I can say that set S is equal to set T because not only do they have the same cardinal number, but they have the exact same elements. All right, the last page of this section of notes. Equal sets. Set A is equal to set B means that they contain exactly the same elements regardless of order. So, are these first 2 sets equal? Well, no, they are equivalent because they have the same cardinal number, but they're not equal. I could say set S does not equal set T. What about on the second option for B? Yes, these are equal sets. C? Yes, these are also equal sets because, again, not distinct elements. So they would have the same cardinal number. All right. 4 sets here, all labeled set A. Oh, A and B, A and B, A and B. For the first line, let's do this. 1, 2, 3, 4. For number 1, are the 2 sets equivalent? Do they have the same cardinal number? Yes, the cardinal number is 4 for both of them. So I say the cardinal number of A is equal to the cardinal number of B, and that is 4. Are they equal? Well, no, because they don't have the same elements in each set. What about for number 2? Are they equivalent? Well, no, because the cardinal number of set A is 3 and the cardinal number of set B is 4. If they're not equivalent, then they absolutely cannot be equal. What about number 3? These two are equivalent because if I look at their cardinal number, they have the same cardinal number. They both have 4 elements. And they are equal because those elements are the same 4 elements. And finally, number 4, are these two equivalent? Look closely. They are, because they each have 3 distinct elements. The number of A and the cardinal number of B is each 3 because B only has 3 distinct elements. Because of that, and because they are the same elements, A does equal B here. So, can 2 sets be equivalent and not equal? Yes, they can. They can be equivalent and not equal. For example, that number 1 is equivalent, not equal. They are the same cardinal number, but not the same elements. Can 2 sets be equal, but not equivalent? Well, no, because if they are equal, that means that they have the exact same elements in each set, so they're going to have the exact same cardinal number.